So in this session, I will discuss the structure questions related to topic KC and KP. The last session, I discussed question 1. So in question 2, methanol is synthesized by the following reaction. Carbon monoxide is mixed with hydrogen and the reaction is reversible. So when they react with each other, as a result, it will produce methanol. In the question, a mixture of 39.5 moles of carbon monoxide and 77.5 moles of hydrogen was allowed to reach equilibrium. So when they are reacting with each other, it reaches equilibrium at 500 Kelvin. That's the temperature at which it reaches equilibrium. And 50 atm. 50 atm is the total pressure. Under these conditions, the equilibrium mixture contains 38.5 moles of methanol. Write an expression for the equilibrium constant in terms of Kp. So Kp means in terms of pressure, we have to write the expression here. So that is a product divided by reactant. So pressure of the product. So what is the product here? We have methanol as a product. So that is CH3OH divided by the pressure of the reactant. We have carbon monoxide and we have hydrogen. Because it is 2H2 here, it is 2H2, so means this will be power 2 or twice. So this is a expression for Kp. Now the next part, we have to complete the table here. The moles at the beginning are given. Like in the beginning, we were having carbon monoxide, and you need an equation for that. So we have carbon monoxide and hydrogen form methanol. In the beginning, at the start, we were having 39.5 moles of carbon monoxide and 77.5 moles of hydrogen, and there is no moles of methanol. But at equilibrium, we have 38.5 moles. So how many moles? It's not like how many moles are reacted, it's how many moles are left at equilibrium. So what we will do, we'll take a ratio between, like to get the moles of carbon monoxide, we can take a ratio between carbon monoxide and methanol. So according to equation, the carbon monoxide and methanol, the mole ratio is 1:1, according to equation. So if we have 38.5 moles of methanol are produced, then X moles of carbon monoxide will be there. When we cross multiply, the value of X is 38.5. So it means 38.5 moles of carbon monoxide are used or reacted, but we write how many moles are left at equilibrium. So if originally it was 39.5 and reacted 38.5, so what is the difference? 39.5 minus 38.5, so it will be 1 mole. Same thing, we will take a ratio between hydrogen and methanol. According to equation, the ratio between hydrogen and methanol is 2:1. So if 38.5 moles of methanol are there, X moles of hydrogen will be. So we cross multiply, so 38.5 will be multiplied by 2. That will give us 77. So the 77 are the number of the moles which are reacted, but we are not finding how many moles are reacted. We are finding how many moles are left at equilibrium. So if original were 77.5 and out of that 77 reacted, so how many moles are left at equilibrium? It will be 0.5 mole or half mole of hydrogen will be left at equilibrium. Then what is the total number of the moles? So we just sum here 1, 1.5 and 38.5, so that will make 40. So total number of the moles which are left will be 40. Like the total number of the moles for reactant and product. And using this, we can work out the next part, like when the reaction is carried out at 700 Kelvin and 50 atm, the value of the Kp is smaller. Use this information, reduce the sign for entropy of surrounding for the forward reaction and justify your answer. So when we have a high temperature, the Kp is smaller. So what is the relation between if the reaction or a forward reaction is endothermic, or if a reaction is endothermic, a reversible reaction is endothermic, when we increase the temperature, the Kp will also increase. So for endothermic reactions, the Kp or the Kc is proportional to temperature. Increase in temperature, increase the value for Kc or Kp. But for exothermic reactions, what will happen when we increase the temperature? If the forward reaction is exothermic, when we increase the temperature, the value of the Kc or the Kp will decrease. So as you see, when the reaction is carried out at 700 Kelvin and 50 atm, the Kp is smaller. So if the temperature is high and the value of the Kp is smaller, so what it gives an idea? This gives an idea that this reaction is, the forward reaction is exothermic. So the forward reaction is exothermic. And the total entropy is related to R, ln K. And how the total entropy is given by? The total entropy of is given by entropy of the system, that is the reactant product minus reactant, plus the entropy of the surrounding, which is minus delta H by T. So we can say the total entropy is equals to entropy of the system, which won't change, minus delta H by T. And if the reaction is exothermic, what will be the value for delta H? The delta H will be negative. So if the delta H is negative, so entropy, the total entropy of the system will be, this will become, because if delta exothermic reaction, delta H will be negative, so minus minus plus. So it will be plus delta H by T. So what happened to the total entropy as we are increasing a temperature? When the reaction is exothermic, when we increase the temperature, this entropy of the surrounding will decrease. If the entropy of the surrounding decreases, because system is constant, so surrounding is decreasing, so sum of system plus surrounding will also decrease. So, and if the total entropy decreases, what is the relation between entropy and the K? That total entropy is equals to R, which is a constant, ln K. So it means if the total entropy increases, the ln K or the value of the K will also increase. If the total entropy decrease, the value of the K will also decrease. So it's of 2 marks. 1 mark when you mention as we are increasing a temperature or a high temperature and lower value of a K, means the forward reaction is exothermic. And when the forward reaction is exothermic, the entropy of a surrounding, which is given by minus delta H by T, will be positive. But because the temperature is high, so the entropy of the surrounding will be low. As a result, the total entropy will decrease. And when the total entropy decreases, the equilibrium constant or K will also decrease. Is it clear, this question? The relation between the total entropy and the value for K? The part D is related to the organic chemistry that we will discuss after equilibrium constant question. Next is question 3. So ethanoic acid and ethanol react together to form ester ethyl ethanoate. So ethyl ethanoate is the expression for Kc for this reaction. So what will be Kc? Kc is equals to the product divided by reactant. So what is the product? The product is the concentration of CH3, COO, CH2, CH3, And this is a homogeneous equilibrium. So like all are in the same state. So we will include all of them divided by the concentration of reactants. So CH3COOH and CH3CH2OH. So Kc will be the product divided by reactant. By considering the effect of temperature on entropy change of a surrounding suggests why the changing temperature has a little effect on this equilibrium. Like when we change the temperature, it does not affect this equilibrium too much. So what is the reason for that? As you can see, the enthalpy change or a delta H is very small in this one. Like this reaction is slightly exothermic, as you can see here. So when we change the temperature, so we have the because by considering the effect of temperature on entropy change of the surrounding suggests why changing a temperature will have little effect on equilibrium, like why the value of the K does not change. So the total entropy of the reaction is given by entropy of the system, which is constant because it depends on the reactant and the product. So the entropy of a system is constant plus entropy of the surrounding. And here in the entropy of the surrounding is minus delta H by T. So we can say the total entropy is equals to entropy of the system minus, and the forward reaction is like, because entropy of the surrounding is minus delta H by T, but if reaction is exothermic, so minus minus will be plus delta H by T. Now, because this value is very small, so even we increase the temperature or decrease the temperature, like already the value is small. So by changing a temperature cannot change this factor too much. So as a result, what will happen? The total entropy won't change much. Like if, for example, if the delta H is like say 0.00001 and I divide by 300, I divide by 310, I divide by 400, that does not make much difference to, because the value is already small. So even I divide with a small or a large number, it does not make too much difference to the final value. So the delta H is very small as a reaction, as you can see here, minus 3.5. So it's a very small value for enthalpy change, or it is less exothermic. So as a result, when we change the temperature, the total entropy won't change. And as the total entropy won't change, the formula which relate the total entropy is equals to R ln K. So if the total entropy is not changing, what happened to the value of the K? That will also remain unchanged or constant. So the points which you should include, that the enthalpy change is very small for this exothermic reaction. And so by changing a temperature, the entropy of the surrounding won't change too much. As a result, the total entropy will remain more or less constant. And as the total entropy remain constant or very small change is there or negligible change, the value of the K will also be same. Is it clear, the second part? Okay. In an experiment is carried out. So an experiment is carried out to determine the value for the Kc. So Kc is a product divided by reactant, and the concentration of the product divided by concentration of the reactant. We have 0.12 moles of ethanoic acid, because in the reaction ethanoic acid is added to ethanol to produce ethyl ethanoate plus water. Then 5 cm cube of 1 mole per dm cube hydrochloric acid is added as a catalyst, which contain 0.278 moles of water. So initially we have this many moles. The mixture was left at equilibrium. The mixture was titrated with sodium hydroxide, which react with both acids. Like it react with ethanoic acid, it react with hydrochloric acid. The titer was 45 cm cube, like 45 cm cube of sodium hydroxide was needed to completely react with both acids. We have to determine the value for Kc. But to determine the value for Kc, we should know the moles at equilibrium for the product and the reactant. So these are the initial moles, 0.12 moles of ethanoic acid and 0.220 moles of ethanol. So, and we have hydrochloric acid is there. So first we'll find them, because now how many moles of hydrochloric acids are there? Moles of HCl, moles equal concentration into volume. The concentration of the hydrochloric acid that is given 1, and the volume is 5 cm cube, so we have to convert into decimeter cube. We divide by 1000, so it will be 1 divided by, this was 5, so the moles of HCl 0.005, so when we multiply we'll get the same, 0.005 moles of HCl. So first what happened, like how many moles of total sodium hydroxide moles were there which are added? These sodium hydroxide moles reacted with hydrochloric acid and reacted with ethanoic acid, both of them, and that will be the moles of ethanoic acid at equilibrium. So we have the reactant ethanoic acid reacted with ethanol C2H5OH. So ethanoic acid reacted with ethanol produce ethyl ethanoate plus water. So in the beginning we were having 0.12 moles, 0.220 moles. This was 0 and the water moles were 0.27. Now what happened when we add sodium hydroxide? Sodium hydroxide react with the hydrochloric acid, which was a catalyst for the reaction, and it also reacted with ethanoic acid. So first hydrochloric acid, because 0.005, and how many moles of sodium hydroxide were there? This is 1 and the volume is 45. So it will be 1 into 45 divided by 1000. So this will give us 0.05 or 45 moles of sodium hydroxide. Now, when you check the ratio between sodium hydroxide, write a balance equation, you'll find the ratio between them is 1:1. Like 1 mole of sodium hydroxide reacted with 1 mole of hydrochloric acid. So ratio between them, the sodium hydroxide and hydrochloric acid is 1:1. So 1:1 is a ratio. Because the limiting reagent like 0.005 moles are there, then this will be X. Cross multiply. So how many moles are needed for sodium hydroxide? 0.005 moles needed. But we have 0.0045. So out of these are the total moles of sodium hydroxide, and out of this 0.045, we use 0.005. So how many moles of sodium hydroxide are left after reacting with hydrochloric acid? So this 0.045 minus 0.05, this will give us 0.04. So these are the moles of sodium hydroxide left. And these moles will react with ethanoic acid. So and then when you write an equation, you will find the ratio between them is 1:1. So 0.04 moles are reacted with ethanoic acid and 0.005 moles are reacted with hydrochloric acid. Because the ratio between them is 1. These are the total moles of sodium hydroxide. 1:1 is the ratio. So hydrochloric acid reacted and then ethanoic acid. So it means the moles at equilibrium for ethanoic acid were 0.04. And now, so these are the moles of it, as the sodium hydroxide is reacting with both of them, so it completely removes hydrochloric acid and then it completely removes ethanoic acid. So This was the initial moles, like in the beginning, and these are the moles at equilibrium. So moles at equilibrium are 0.04. Now, after getting the moles at equilibrium, we'll try to complete the table. Now, what is the ratio between ethanoic acid and ethanol? The ratio is 1:1. So how many moles of ethanoic acid reacted? So how to know how many moles are reacted? Like originally it was 0.12 and now it is 0.04. So it's 0.12 minus 0.04 will give us how many moles reacted. So 0.08 reacted. And the ratio between them is 1:1. So if we have, like this was the moles for hydrochloric acid and sodium hydroxide. Now we are finding the moles of ethanol. So how to work out the moles of ethanol? Originally, this was ethanoic acid and finally at equilibrium 0.04. So how many moles reacted? Means 0.08 reacted. So the ratio between ethanoic acid and ethanol is also 1:1. So if we have 0.08 moles, so then it will be X cross multiplied, so 0.08. Means 0.08 moles of ethanol reacted, but we are not finding how many reacted, we are finding how many left. So 0.22, that was the original moles, minus 0.08. This will give us 0.14. So 0.14 moles of ethanol are left at equilibrium. Is it clear till this point? That how I worked out. So using the sodium hydroxide, we worked out how many moles of ethanoic acid are there at equilibrium. Then using how many moles of ethanoic acid reacted, you use a ratio to work out how many moles of ethanol are there for this reaction, which are reacted, and remaining, which because 0.08 reacted, so when we take a difference, 0.14 moles are left. And then we take a ratio between ethanoic acid and ethyl ethanoate. Again, they have the ratio 1:1. The ester CH3COO C2H5. So 0.08 will be X. So when you cross multiply, it will be 0.08. And then about the water, we already have this many moles. When we take a ratio between water and ethanoic acid, it's 1:1. So we'll get the same moles of water, 0.08. So originally we have 0.72 plus 0.08, 0.278 plus 0.08 will give us 0.358. So 0.358 moles. So these are the moles at equilibrium. Is it clear how I worked out the moles first? The total volume of the solution is not given, so we can, because to get the concentration, these are the moles at equilibrium, we need a concentration. To get the concentration, we divide by volume. But here, this question, it does not make difference. Why? Because I can also substitute the moles, I will get the same answer. Why I will get the same answer? Because when we write the expression for Kc, which is a product divided by reactant, so if I write there, if I say the total volume is V here, total volume of the solution is V, so we divide all of them by V to get the equilibrium concentration. Now, when we write the expression for Kc, which is a product divided by reactant, so ester is there, water is there, ethanol, ethanoic acid is there, and alcohol. So this is moles divided by volume. This is also moles divided by volume, moles divided by volume, and moles divided by volume. So all the volume will cancel each other. They have different moles, but the volume unit will be cancelled. Like the Kc will not have any unit. That's why we can also substitute the moles instead of the concentration. Why? Because if the Kc does not have unit, it does not make difference what we substitute. We can substitute moles, we can substitute concentration. So we just substitute the moles here for the product divided by the reactant, which is 0.04 and 0.14. So when we simplify, this will give us the value for Kc. Which is a very high value, about 5.1. So these type of questions are common in exam, so 5.11 and with no unit, because as they cancel out each other, this will not have any unit. In question 4, ethanoic acid and ethanol react to form the ester ethyl ethanoate. We have to write the value for K, the expression for Kc. So it's a homogeneous equilibrium, like all the reactant products are in the same state. So we have CH3, COO, CH2, CH3. Then H2O water is there, divided by CH3, COH, and then CH3, CH2, OH is there. So Kc is a product divided by reactant. Then an equilibrium was reached when the amount of the substance shown in the table, complete the table, shows the amount of each substance present at equilibrium. You can see the ratio between them is 1:1. Now these are the moles at equilibrium. So moles of ethanoic acid are given. So how many moles? We don't check how many moles are there at equilibrium. We'll check how many moles reacted. If original moles were 0.4 and at equilibrium we have 0.2, so how many moles are reacted? It means 0.2 moles of ethanoic acid reacted. As you can see the ratio between them. So 0.2 moles are reacted. So when now we take a ratio, all of the ratios are 1:1. So we'll find the ratio between ethanoic acid and ethyl ethanoate. The ratio between them is 1:1. So if we have 0.2 moles, so this will be X. We cross multiply because this 0.2 is not, I'm not using 0.2 moles at equilibrium. I'm using how many moles are reacted. So 0.2 moles are reacted. So cross multiply. So 0.2 will be there, the same answer. But what we write here, we write how many moles are left. So these are the original moles minus the reacted. So 0.3 minus 0.2. How many moles are left at equilibrium? 0.1. Same thing, the ratio between them is 1:1. So 0.2 moles will be produced and originally it's 0. So 0 plus 0.2. So it will give 0.2. Then we'll take a ratio 1:1 again, the ratio. So same number of moles 0.20 will produce and already we have 0.15. So 0.15 plus 0.20, it will be 0.35. So these are the moles at equilibrium, 0.2, 0.1, 0.20 and 0.35. Explain why Kc of this reaction does not have any unit. Like it's the same thing. So what is the reason for that? Because the units cancel out each other, or there are same number of moles for the react, like numerator and the denominator. That's why. Or you can also mention volume can cancel out, like same number of moles or same number of molecules in each side. Like reactant and product, they have the same. Like in reactant side, we have 2 molecules. Product side also 2 molecules. That's why they cancel out each other. So that's a reason why there is no unit for this case. Then state the numerical value of a Kc. So after getting this answer 0.2, 0.1, 0.2, 0.35. So Kc will be the product divided by reactant. So we substitute the concentration, like these are the moles, but concentration, like it will be 0.20 divided by volume. Then it will be 0.35 divided by volume. That is a product divided by reactant. 0.20 and 0.1. So 0.20 divided by volume and 0.1 divided by volume. So this V will cancel. So we are left with only moles. So I can directly substitute the moles. So the answer for this one is 3.5 with no unit. Esterification reaction above can be carried out in the presence of hydrochloric acid as a catalyst. State an effect on equilibrium position and the rate of attainment of equilibrium if the concentration of acid catalyst were to be increased. So look, Kc or Kp is not, it's only affected by temperature. Like when we change the temperature, even I add acid, I add reactant, I add product, the value of the Kc does not change. So there will be no effect on the value for Kc or Kp. So no effect on the value of the K. But what will happen as we increase, like we add catalyst, the particle, because catalysts increase up the speed of reaction. So as a result, what will happen? The rate of the collision increase or equilibrium will reach equilibrium in a short time, but it does not affect the value. It will not affect the value for Kc or Kp. So no effect on Kc or Kp. The only thing which affect is the rate will be affected. It will be faster, or we can say we can reach the equilibrium in a short time. So reach the equilibrium faster. In question 5, hydrogen can be manufactured by reacting methane with steam. As you can see, the reaction, forward reaction is endothermic. The standard entropy of 1 mole of hydrogen is given, and entropy of 1 mole of water is also given. You will also need to refer the data booklet. The data booklet is important. So calculate the standard entropy change of a system. So how to calculate the entropy change of a system? Entropy change of a system is a product minus reactant. So when we subtract the entropy of a like from a product and reactant, we got the entropy change of a system. So the product is, and you have to use a data. The product is hydrogen is there. Like for 1 mole of hydrogen is this much. But how many moles of hydrogen are there? There are 3 moles of hydrogen, so this will be multiplied by 3. Because when 1 mole is there, 130. So the entropy of a system is a product minus reactant. So this will be 3 times the product is 130.6 plus carbon monoxide. For carbon monoxide, carbon monoxide and methane, you have to use a data booklet. So I will write the value directly. For carbon monoxide, it is 197.6, but you have to use a data booklet. Minus for reactant, 197.6 is there for reactant, so it is 186.2. That is methane, and 1 mole is there plus 188.7. This will be the reactant and product. When we simplify, we'll get the answer in 214.5, but that is Joule mole inverse, Kelvin inverse, because the values here are given in Joule mole inverse, Kelvin inverse. Then we divide by 1000 to convert into kilojoule, or you can write it in this manner. That's also fine. The sign is important. The entropy change for this system, it's coming out positive, so you have to mention write a positive sign. Like don't write, because entropy change can be positive or negative, so you should mention that it is a positive. Then entropy, calculate the standard entropy change of a surrounding. So how to calculate for surrounding? Delta H by T. That will give us an entropy change of surrounding. And enthalpy change. And one more thing, the enthalpy change are always given in kilojoules, so don't forget to convert into joule. Like here, the value for delta H It's given in kilojoules. So don't forget to convert into joule. So kilojoule to joule, you will multiply by 1000. So we'll substitute the value. It will be minus 206 multiplied by 1000 to convert into joule, and 20, like room temperature 25 degrees centigrade or 298 Kelvin. So when we simplify, it will give us minus 619. Why this 1000 is multiplied to convert this kilojoule, the unit of enthalpy change from kilojoule to joule. So 619.6 will be there. Joule mole inverse Kelvin inverse. And then the total entropy, that will be the system plus surroundings. Our answer for the previous B1 and B2. We just sum. So 214.5 was there, the first one, plus the surrounding is minus 691.6. So when we simplify, we get a negative answer, minus 4.47 joule. This one is 477. That was in kilojoules. So 477 joule mole inverse Kelvin. So the enthalpy change is negative. What it gives an idea? It gives an idea that this reaction is thermodynamically not feasible, like it's not non-spontaneous. Then we have the expression for Kp. So quickly, I'll go through this. Just write an expression for Kp. Here, Kp will be the product, and then calculate. The total pressure is 2. That's the total pressure. So we'll find a partial pressure. How to get the partial pressure of methane? Moles of the gas divided by sum of the moles, like the total number of the moles. So we add the moles of the reactant product, that will be the total moles, and into the total pressure. So this will be 0.8 plus 0.8 plus 1.2 plus 3.6. So total moles are 6.4. And then multiplied by total pressure 2. So 0.8 multiplied by 2 divided by 6.4. This will give us 0.25. So the pressure of methane is 0.25. Same way the pressure of the water will be there. The moles of the water 0.8, total number of moles remains same, multiplied by 2. So we'll also get 0.25. We'll write the expression, and then the pressure of carbon monoxide, that is 1.2 divided by total 6.4 to total pressure 2. So 0.37. And then pressure of the hydrogen, moles of hydrogen at equilibrium, that is 3.6 divided by 6.4 into total pressure. So hydrogen will have the highest pressure, partial pressure, because it's having the greater number. Then we write a expression for Kp, which is a pressure of hydrogen, carbon monoxide divided by pressure of methane and water. This will give us the value for Kp. Is it clear, this one? And then the total entropies are L and K. So we can just substitute the value for Kp to get total entropy and calculate the temperature at which the equilibrium, the total entropy is for, assume the delta H is 206. So at what temperature this reaction will become thermodynamically feasible? So we'll consider that the